Good afternoon, all. So, welcome to this Samvaad session. So, today we have Professor Aswin Kannan. So, Professor Aswin Kannan is currently an assistant professor at IIIT-Bangalore. Previously, he was a faculty member and group leader at Humboldt University of Berlin in Germany. He holds a doctorate from Penn State, US in 2014, and a master's from University of Illinois at Urbana-Champaign, US, both in industrial engineering, and a bachelor's from College of Engineering, Guindy, India. Even earlier, he had worked in the US and India for IBM Research from 2015 to 2021, Oracle Analytics from 2014 to 15, and Argonne National Labs from 2010 to 2012. So today he'll be talking about data-driven multi-objective optimization in energy systems and analytics. So over to you.
Thanks a lot, Professor Raghu. Yeah. So I'll actually I'll get started. So today we are just going to focus on a class of these optimization and machine learning problems that are inherently multi-objective in nature, and which are actually common to energy systems and analytics. So we do have a lot of other applications as well, but I'm just focusing on the last, rather a few facets of my work over the last few years. So in short, this is the overall agenda of my lab, what problems we are kind of interested in. So to just cut a long story in short, we are looking at multi-objective optimization problems where you are not just trying to minimize or maximize one objective, you're trying to look at multiple such objectives of interest. And of course, the main aspect that I'm kind of interested in here is that these problems are coupled with a learning problem. So I could give you some examples, right? Suppose you have some data on weather, and we'll focus on this a little later, but you have some weather data, and you are trying to come up with some predictions as to what the next day the solar or wind energy output is, and based on which you're trying to optimize some other problem on planning reserves or on maintaining some generation levels or minimization of something. So that is sort of an example where this comes about. So we'll focus a little on the applications, the modeling aspect, and then we'll also focus a little on the theoretical aspects on algorithms that we are trying to propose. And I'll also hint some thoughts for the future work. So, and vaguely, in a more pictorial sense, this can be represented as follows. So when we're looking at combination learning and optimization problems, so we are, what we're trying to do is, there are, if you've heard about model-based methods like trust region methods or Bayesian methods, and there are some search-based methods like direct search and elder meet, we're trying to fuse both of these. We're trying to see the benefits of both of these worlds. That's from a theoretical standpoint or algorithmic standpoint. From an application standpoint, these cover a lot of applications in energy markets where you have policy design, you have game theoretic problems, and you have machine learning problems. And of course, you have business analytics also, where you find a lot of these problems in retail spaces and workforce, and possibly also industrial safety and all those things. So I'll just quickly go into the problem of energy in the space of energy and analytics for this talk, as I was mentioning. So to just give you a quick overview. So I mean, is everyone, or at least is a subset of audience, aware of multi-objective unit commitment or unit commitment at all? I would, yeah, okay. I would take no as the answer. So unit commitment refers to just a very typical power dispatch problem. Suppose I'm now sitting in Bangalore and I have some generators and I have some oil, coal, or I have some wind energy generators. I'm trying to just dispatch power from Bangalore to Delhi and Bangalore to, say, Chennai. And I'm trying to maintain a supply demand balance here. So whatever I generate has to be dispatched. And at the same time, whatever I dispatch has to be consumed. And I also have to make sure that transmission constraints have to be met. And one of the major disadvantages, a lot of people don't know much about it, is that coal generators operate very differently. So let's ignore the slides for a minute. So if I switch on a coal generator, it can't be switched off immediately. So it has to run for a certain amount of time. But that is not the case with wind and solar generators. You can switch them on and off anytime, but of course, their intermittency is a huge issue. So generation cost minimization is one part that we all have to think about. At the same time, you can't keep operating with coal generators all the time. They're quite reliable, but they come at a huge cost of emissions. So you have to reduce carbon emissions. And the main thing I'm trying to mention here is a host of all these previous approaches have focused only on single objective problems. They've not worked on multi-objective problems. So that's the key intent of my work. So we are trying to extend these to the cases of multiple objectives. So, and of course, this also involves, as a second bullet point here denotes, you have to come up with a lot of predictions. So you can't just like that come up with a statement on saying, okay, I'm going to have this much of coal and this much of renewable energy in my mix. You need to know what your target, or rather what is the maximum that you can produce with wind and other renewable energy generators. So coming up with smart predictions based on data is a very crucial problem, which we will also focus on. And lastly, again, I'll just mention that from an analytics standpoint, the exact formulations that we see here for energy can also be are sort of replicated even in retail and other analytics related applications. So that is another reason why I'm focusing on this. So prior to just getting into the actual problem, I'll define what a Pareto frontier is. So this is the notion, or rather the key notion for optimization in the space of multiple objectives. Say, just as a very normal example, I'm looking at minimization of two objectives here. Suppose I'm telling you that you have to choose a machine learning model, which is good from a standpoint of accuracy and also very good or efficient in terms of computational effort. So you're trying to just compute what the Pareto frontier is in this case. So that sort of is the best of, rather the best trade-off between the two objectives. The Pareto frontier denotes that actually. So you see that moving from one point here on the blue region, you move from one point to another, you kind of can't, rather you have to compromise in one objective to get a better value in another objective. Say for instance, if I have very computationally efficient model, it's going to be very bad in terms of accuracy. On the other hand, a very something that takes a long time is going to give me very good and accurate solution. So you have to find the trade-off, or rather this entire trajectory of points, which are one is actually not better than the other, but it is just that you have to compromise in one of the objectives. So that is pretty much what we're looking at in terms of the Pareto frontier. So, and how do we measure this Pareto frontier, or rather quantify how good the Pareto frontier is? So say for instance, this A1, A2, and A3, all these 3 points are good. So you see that moving from A1 to A2 comes at a compromise in objective F1. In order to do better in F2, which is decrease F2, you have to increase F1. So these points are quite good, but what is your reference? How do you say that this Pareto frontier is good or bad? For which you have to look at something called the worst case point, which is your reference point. And the reference point is actually completely the opposite of what you're ideally looking for, which is 0, 0 when you're trying to minimize two objectives. And you're trying to come up with this particular region, which is captured between the reference point and all these points together. So that's pretty much what you intend to maximize when you're looking at a multi-objective optimization problem. We call this the hypervolume indicator. There are other indicators too besides hypervolume, and one is hypervolume, and this has been quite robust. So, okay. So now getting to the unit commitment problem, as I was mentioning, I've put in a very simplistic view of the problem here, but nevertheless, it's a mixed integer optimization. Yes. No. More the hypervolume, better the solution is. So 0, 0 is your ideal point, and yeah, 0, 0 is ideal. Reference is the worst case point, which is opposite to your opposite. It's completely, that's called as the Nadir point, which is the opposite. So, I mean, They call it nadir because in optimization they kind of assume minimization is the norm, and yeah. 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 That's a good question. Nash equilibrium is you. So we do focus on Nash equilibrium problems also. There's only in most of the cases I would say there's one equilibrium solution for all agents. It might not be the best, but it is one equilibrium solution. In the space of optimization, at least, there's a pure, exactly. So that is true. So it's sort of very similar, but at least in several cases, you have agents who take their own independent decisions. Say, if I'm agent one, you're agent two, and your decision is independent of my decision. But in multi-objective optimization, a priori. Yeah. Yeah. That is true. That is absolutely true. So they are kind of, I would say, multi-objective optimization is just one generalization of game theoretic problems. But game theoretic problems are more involved in that it's harder to find an equilibrium solution. These are a lot easier. So that much I can say. These are a lot easier. So you take two weights and you combine two objectives, you get away with this. But in game theory, you can hardly do that. You need to, as you rightly mentioned, you need to know the other person's strategy in order to find your best. So that's how I would look at those things. But there is another catch, at least in when you're looking at continuous strategy games, when you have convex, I mean, at least the theory is restricted to convex continuous theory games. But multi-objective optimization, you do focus on non-convex problems, and it's a lot easier. Yeah, that's another difference I would like to point. Yeah. They are contradictory in multi-objective more. So one clarification, that's a good point. In game theory, that is also the case. In multi-objective optimization, also you end up optimizing only contradicting objectives. But the catch is they need not be always contradicting. So I agree. I sort of agree in that sense. Yeah. So when you say sorry yeah is decreased and the other is increased. Yeah. They are sort of contradictory. Most of the cases, it is 90%, or I mean, that's exactly. Have only one. There's no agent. There's only one person, and who's trying to optimize. Yes, absolutely yes. Yeah. Yeah.
Since these multiple, so based on each objective, the point that we get to vary. So what do we call it as a best optimal? For every objective, and it is important to every objective the graph keeps changing.
Correct. So no, the graph. Yeah, go on. No, reference actually is okay because that is a worst case point, right? So that is only one point. So that is not hard to figure out. But you're right in that there is no one solution which you claim is the optimal solution. It's a family of these solutions. So the one thing, the best we can claim is all these points, right? They are called as dominated points. Or rather, you move from one point to another. Say, for instance, you look at this point, or rather you look at this point and you compare this point. This is better in both objectives when compared to this point. So you say that this is the family of solutions, which is the set of non-dominated points. So that is the only difference. Other than that, I don't think there is going to be one single solution. So at least in game theory, you have a lot of cases where you will have a unique solution. I mean, you do have non-unique solutions also, but nevertheless, at least. Yeah. No, we want to find this. That's pretty much it. So it depends on. So I can give you an example, right? Suppose let's just change these axes. Let's have generation costs on the x-axis and carbon emissions on the y-axis. You want to minimize both. Ideally, 0, 0 is great, but nothing happens, right? So the issue is you have to find out this trajectory. If someone puts a law tomorrow saying, I want to have emissions less than, say, 0.4, whatever the units are, tons of carbon or whatever. So I would say that I'm not interested in this trajectory. I'm just interested in these points which are optimal from both angles. So that's how I would look at things. They are very important in policy design. Yeah. Trade-off, yes.
Choice on where on the front you need to be, that is not done with the algorithm design, that's done with the user.
It's done by the user. That's completely a practitioner. Yes, yes, that's completely a practitioner's perspective. So that is something that, yeah, you would finally want as a user. Algorithm just figures out what this Pareto frontier is. Yeah. Yeah. In games or games, bounded rationality automatically say in two settlement markets or
Yeah.
yes, but here there is no concept of rationality in the space of multi-objective optimization. It's just plain optimization. So when you're talking about Nash versus Nash-Stackelberg, the bounded rationality thing sorts of kicks in Nash, and it doesn't kick in Stackelberg. So I understand, but here I don't think it even is important because we don't. It's not that hard. So yeah, multi-agents setup. Yeah,
It's basically about how you want to react, having seen what the move the other person.
who the other person
Whereas
takes.
it's
It's a single agent.
no notion of
Rationality. Yeah, yeah. It's just plain. Yeah, it's vanilla optimization. That's it. It's just that you have to figure out a way of putting all the objectives together. That's all. So, okay, I'll just get back on this. So, the main thing is this is a mixed integer optimization problem. I've not gotten into those details, but just to give you an idea, when you switch on a coal generator, you can't switch it off the next 2 or 3 hours. So this has to be modeled by an integer variable or a binary variable. On a similar front, if you switch it off, or rather, if you switch it on immediately, you can't switch it off. So it's both constraints. So also, once you've started, say you're generating 2 or 3 megawatts of power now, you can't go immediately to 10 or 15 megawatts of power the next hour. So there has to be certain limits. These are called ramp limits. So you can't ramp up to 5 or 7 immediately. So those constraints are all going to be there when it comes to optimization in unit commitment. So I have very simplistically mentioned some discrete variables here for on-off and some linear constraints for taking care of all these ramp constraints and running constraints. Some generators are on-off and running denotes, 0 indicates it's not running, 1 indicates it's running, and so on and so forth. So, and of course, you have generation costs, which are, at the moment, we are looking at only convex costs where it's either quadratic or exponential. We are not going too much into the non-convex world, at least in this particular work. So here, objective F1 is nothing but your generation cost, and F2 is nothing but your carbon emissions. So this is pretty much what we're looking at. So the main novelty here is that most of these works have considered only single objective problems. They've not done any multiple objectives, or they've not worked on it. So that is giving us the scope for optimization. So anyway, so the main way how we do optimization is we agglomerate, or rather we group all the objectives into one. So using some weights. And these weights, we allow, say 0.1 times f1 of x plus 0.9 times f2 of x is one example. 0.2, 0.8 is another weighted combination, so on and so forth. So how do you choose those weights? You can have infinite weighted combinations. So you could have so many combinations, and figuring out all the solutions, or rather solving all the optimization problems, is going to be super tricky. It's going to be very computationally expensive. So we have to figure out a way where we don't examine all weights, we just examine a subset of weights. And the main thing which I'm trying to which I've not mentioned here, but which is important, is once you put in a fewer choices of weights, coming up with the right weights involves actually imposing another quadratic constraint into this model. So which I've not shown. What happens is once you know these weights a priori, things are great. But there are cases where you don't. So you want to just instead of looking at the exhaustive space of between 0 and 1, you look at some stylized cases and you impose a quadratic constraint to just figure out what those weights are. So you have another quadratic constraint that shows up here. So, and that ends up to be a further complicated problem, but the advantage is it's in only one objective. It's a single objective optimization. So now, but let me, F1 and F2 are convex. That is not a problem. But weights are chosen a priori anyway, prior to optimizing any single objective problem, irrespective of whether I'm using adaptive weights or whether I'm using non-adaptive weights. So why this comes up is, you suppose you optimize with 0.1 and 0.9, for instance. That's a convex problem. And for the next iteration, you want to come up with a better set of weights which are not just 0.2, 0.8. And that is based on what your evaluations are, or your objectives F1 and F2 are post your solution. For which you actually say, for instance, you get these 2 points. Instead of looking at a uniform distribution and choosing another way, you impose a quadratic constraint which is dependent only on X, not on W's. No, there are only one set. So there's only one set of variables, which is X. W is not my variable. W is just fixed a priori. X is nothing but your decision variables on how much to generate and when to start start your coal generator, when to switch it off, and how much to ramp up, how much to ramp down, all those things. So it is 3 sets of variables. One is your generation levels, one is your running variables, one is your on-off variables. That's it. So just to get this clear, so we are so once you have some quadratic constraints, this problem becomes very tricky. So what we do is we impose what we call as McCormick relaxations. So I think you are familiar with that, where you replace the quadratic constraint, or rather you sort of relax the quadratic constraint by means of piecewise linear envelopes. So essentially you have 4 lines in this case. So instead of just looking at this curve, which is an equality constraint, you put in 4 lines, which are inequality constraints, and you put in this envelope. So, and to make it more tight, you actually can divide this further. You could have two sets of envelopes, and to even more tight, you have more. So you could keep doing that slowly. So the biggest thing that we figured out here was there was nothing. The McCormick envelopes are not novel. That has been deployed for ages, and unit commitment has been solved for ages. The only novelty in our case was we put in adaptive weights, and we rather, instead of scanning this entire region of weights between P1 and P2, we were doing something smart by looking at some piecewise linearizations based on function values. And on top of it, we did something with McCormick envelopes. That's pretty much the novelty we had. So, I mean, we were not reinventing the math here. It's just about putting in the existing known concepts to multi-objective unit commitment. That's pretty much it. So what we observed was, in this case, you see that there's 3 different things. One is your traditional solver quadcon, which is your GURO-B if you've used it for integer optimizations. And the single layer and 2-layer McCormick, what I had just shown here. One is this full guy, which is a single layer, and this is the 2-layer McCormick. And in this case, we see that you had a very impressive performance in terms of using McCormick relaxations. By this, I mean the red ones here. The blue ones are nothing but your GURO. So, and HV just here means hypervolume, and hypervolume with respect to quadcon or GURO-B, and this is McCormick, and this is McCormick 2, which is 2 pieces of McCormick. So there is some theory here, but I'm not focusing on those. So the theory just says that at the end of the day, when you're increasing the strength of your McCormick relaxations, you get really close to the original solutions. So we have some theory, but I'm not focusing on that. Some extensions. So possibly, I think possibly I was looking for Sachit, or I'll looking for Amit. Sorry. Yeah. Yeah. Yes. So we solve a sequence of single objective optimization problems. That's pretty much what we do. We don't. So there are some constraint programming methods where they look at the space of multiple objectives by itself, but we don't do it. We just solve a sequence of single objective problems. So it is only about how you choose those weights. So in short, it's just about the novelty is just about, instead of looking at say 0, 0.25, 0.5, and 1 in steps of 0.25. Instead of that, I try to do something better based on the function values. Say my function values are quite biased towards the second half of the Pareto frontier. So then I would choose more weights between 0.5 to 1, rather than say, for instance, if my objective F2 becomes very useful and important, and if it's quite dense in F2, my Pareto frontier, then I would choose weights between 0.5 to 1 for W2. And for W1, I'll choose between 1 to 0.5. For instance, 0 to 0.5. Something like 0 to 0.25 would be the focus for W1. 0.75 to 1 would be the focus for W2. Does it make sense? Oh, yes. Okay.
Second level, treat your weights as
There are actually, that's a very good question. There is a paper from 2006 by, even in 2018, there's one by Olivier Weck, and he exactly does this, where you put it as a two-level problem, where in one step you just randomly choose weights, and you try to come up with some x, and based on that x, try to recalculate what your w's are for the next iteration, go back and forth. I have not experimented. Actually, that's a very good thought. Maybe that's a good idea for future. I should do that. So that's the one reason why I was hesitant at doing that was he had a case with about 7 or 8 objectives. My case was just with 2. So it was a very simple case. So I just chose weights in this way. But there's a more complicated case which requires something back and forth between weights and the variables. Yes. For each weighted combination, I'll find a unique solution. For each set of weights, I'll find a unique solution. No, but it's a family. All the combinations of weights, but that is what we're trying to reduce. Don't do the entire scanning. Here, global versus local is not the issue. We have convex problems. So given a set of weights, you're going to get a local solution. Sorry, a global solution. That's not the issue. But we're looking at the family of such solutions for different classes, for different choices of such weights. There is one more complicated aspect I don't want to get into, but the Pareto frontier can be non-convex even if the functions are convex. So that is something which I'm not getting into now, but yeah, yes. 2 or 3 maximum, yeah. As in number of objectives or outcomes? Objectives. Yeah. Back and forth. Yeah. There are some smart ways of doing it actually. So yeah, you don't naturally it's adaptive, right? So based on some weights, you try to figure out x, and based on x again you figure out. I mean, it's just go back and forth. It works. It works. But in non-convex Pareto frontiers, it doesn't. It is still not guaranteed. When the Pareto frontiers are convex, it works. So, but it's not. There's a catch. It's not objectives are convex. It's the Pareto frontiers that are convex. Yeah. So this is another thread. Yeah. it'll be a lot easier than hyperparameter search actually, because hyperparameter search we have discrete things showing up there. This is continuous. It's a lot easier. Yes. So this is one thing on a game theoretic side. I just wanted to quickly. I'm not getting into math or any specifics at all. It's just saying that I also work on some game theoretic problems where you have joint electricity and gas networks. So it is just that it goes back to your point, there are multiple agents in the system who are trying to come up with a Nash equilibrium solution. So we do look into those problems also, but I'm just skipping that in the interest of time here. So we'll possibly just get into my real hyperparameter tuning work, which I've been focusing on for the last, for a long time actually. So, yeah. So again, the one thing that I want to mention, what I discussed in the earlier case was the outer problem of unit commitment, where given some capacities or predictions, you're trying to find out what the ideal dispatch is. But in most of the cases, you don't really know what the predictions are, or rather, you don't know how much of wind your generator can produce the next day, or your solar panel can generate the next day. So that is a consequence of, what ideally we do is we have data. And based on the data, we are trying to fit some machine learning models, be it decision trees or neural networks or anything for that matter. And you try to come up with some smart predictions as to say how much, or rather, say I can give you an example. You have some wind data, you have temperature, you have humidity, you have pressure, you have GHI, which is Global Horizon Index, so on and so forth. And then you have your final column on the wind speeds, say 5 to 10 kilometers per hour, 10 to 15 kilometers per hour, 15 to 20. So all these buckets. So this is a classification problem essentially, a multi-label classification. So you try to fit some, what I do is I fit XT, I am very fond of XT boost or gradient boosting algorithms, and possibly with some classes of neural networks. So I try to fit some machine learning models and try to come up with these predictions. So that is what I do here, and this is the inner level problem. So the main thing that we're trying to look at is how do you fit those neural networks, right? You could have, you can have 5 layers or 100 layers, 200 layers. Where do you stop? So pretty much the hyperparameter tuning comes into picture there, and the number of neurons, of course. And when it comes to decision trees, what is the maximum leaves, or rather the final, in the hierarchy of decision trees, the bottommost part, which has a number of leaves. How many leaves can you limit your tree to? So all those things are hyperparameters. So, and the model parameters here are nothing but your weight. Say in the case of neural networks, what is the weight associated with each neuron? So that is pretty much what we're trying to estimate. So, and so the one thing I had at least figured out was there have been a lot of works in literature which actually just focus on either only hyperparameter optimization or model parameter optimization. So why am I interested in this is because of the two-level setup where you have joint coupling between, so in short, joint coupling between these parameters. So that is the reason why I'm interested in these problems. So be it unit commitment, be it predictions, or be it whatever I'm going to discuss in the future, all those things, they come under this hierarchy, as Professor Agwan mentioned, the two-level hierarchy, and it exactly fits into that. And also, I would take that input for weights, so that also fits in here. So the one thing here is, one thing we figured out was with hyperparameter and model parameter optimization, you can go a bit back and forth. You don't have to solve one problem completely before solving the other. So you can just go back and forth. You can iterate at the hyperparameter level, you can iterate at the model parameter level. We have some theory here, I'll talk about it a little later. But when you do this joint approach, so what we at least figured out was, I think I can make this screen slightly bigger. No. So this is nothing but a conventional hyperparameter optimization, the orange and pink curves. And this is your joint hyperparameter and model parameter optimization combined together. You do actually have an increment, or rather betterment in hypervolume. So when you're doing these two things together, and I'm just plotting hypervolume versus time here. And the other thing that I wanted to show was, of course, when you're looking at single objective optimization, just looking at the extremes. Say, one example could be minimization of precision error and recall error. So I could give you some examples prior to getting into what it means in an energy context. Say there is someone doing a brain tumor surgery, and in a brain tumor surgery, actually, a false positive is kind of considered very bad, right? If you're trying to locate a tumor, and if you actually hit the wrong nerve, it's going to be a problem. On the other hand, in several applications you can do that, but in brain tumor you can't. So the most important thing I'm trying to emphasize is this precision error versus recall error. Precision is nothing but it's tied to false positives, and recall is tied to false negatives. So when you're coupling both, right? So you want to just see it is highly, again, application dependent. So what happens is when you do single objective optimization, you are able to only focus on these 2 points, or you're only able to get these 2 endpoints. But on the other hand, when you do this multi-objective hyperparameter tuning or multi-objective optimization, you're able to locate the entire Pareto function. So which is quite important from an application practitioner's perspective. So what we did in the case of energy here was what the objectives were say your predictions, your wind power predictions. The most important thing is you have to balance reserves and economics. So false negatives contribute more towards costs. And on the other hand, false positives, they actually can lead to bad reserves planning. So if you, by mistake, tell me that I'm going to generate 100 megawatts of wind power more the next day, I'm going to have lesser reserves. And that is going to be a problem. I'll plan my coal and oil accordingly based on what my wind and solar energy is. So that is the crucial part. You have to balance both. It is not like accuracy is the only measure. Specific facets of accuracy are important. So that is why the multi-objective learning is important in our case. So that is the prelude. So okay, algorithmically, what are we trying to do? So so there are 2 things that I would like to mention. One is on that we go a little back and forth between this hyperparameter and model parameter optimization. You take one step of hyperparameter optimization. Rather, you say that you're going to train a neural model with 11 layers. In the next iteration, you say that you're going to train a neural model with 13 layers, something like that. Model parameter optimization, you actually don't entirely train the model. You only take a few gradient steps or stochastic gradient steps, and you stop. So you go a bit back and forth. You update. You warm start the next iteration. You go on back. I mean, that's pretty much how it operates. And now the second contribution is for the hyperparameter optimization itself. Can we do something better? So this is one of my key other interesting one of my main works where you try to combine both model-based methods and search. So by model-based optimization, if you are aware of trust region methods or Bayesian optimization, based on some data points, you try to come up with an estimate as to what your surrogate function is, and you're trying to optimize that surrogate function. That is what we do in Bayesian optimization. And in trust region methods, you use your gradient and Hessian to approximate a function in a quadratic sense, and you keep updating those approximations. So you assume, or rather, you build a gradient in all these cases. But what happens is in search methods, which is very common in direct search or Neldom, you actually use, say, coordinate directions or orthogonal directions to find the next best point. So you don't use the gradients. So can you actually combine both of these methods efficiently? The 2 communities actually don't talk. They have established theory in both algorithms, but unfortunately, this is a very different world and that's a very different world. They don't talk. So we try to fuse both of these together. So what we do is Bayesian optimization is a global strategy where you don't examine local regions. You try to fit a good model to the entire set of points. It may or may not be replicative of your function's behavior, but it finds you an optimal solution in a global perspective. But it will not give you good local jumps. So it will just help you identify a wider spectrum. So in this case, for instance, you're just trying to fit this in a very global sense. It could have multiple minima or whatever. In this case, it doesn't have multiple minima, but I'm just saying this. So direct search, on the other hand, they don't care. They just look at a very stylized local region and try to make some increments and try to move to optimal solutions locally. So if Bayesian optimization takes a long time for training, or rather, if it takes a long time for an evaluation, what we do is we say, okay, stop, move to direct search. And with direct search, the biggest advantage is, at least in hyperparameter tuning, say the iterations, or rather say if I move from 2 layers to 3 layers, or 3 layers to 4 layers, I'm not going to do much of an increment in terms of my model. It's just going to be addition of 1 layer. I can warm start, and this fits perfectly with your coordinate directions. So you increment one, what can I say? One element of your space of optimization variables. And say if you're looking at x1, x2, which you're trying to optimize, you increment x1 or x2 by 1. So that is exactly what this means. So you flip this at a very different angle. You just make this coordinate directions 1, 0, 0, 1. And those are examples of search. So you don't do much of a job here other than warm starting and incrementing by means of some coordinate directions. So that is the advantage. So these are very cheap. Direct search is very cheap. So which we are trying to exploit in this case. So when do we switch back? When direct search doesn't give you descent, and actually when a lot of these search, what can I say, steps have been consumed. So that is what we do in this case. And we have some convergence theory for this as well. I'll talk about it to the end. So anyway, so this is a paper which actually demonstrates some deployment of this algorithm on some real data. We have some points with about, we have some 70,000 data points here, and 23 input features. It's a very simple CSV file. It's nothing more than that. So, and we're trying to figure out what your wind speeds or the solar energy generation is. We've done this across multiple data sets, not just one. So, and the metrics that we're trying to optimize are, of course, your accuracy measured by mean square error or mean bias error. And naturally, we also have, if you've heard about disparate parity difference, that is another metric which is very similar, rather which is replicative of bias in machine learning models. And of course, we have sparsity. We want to have as sparse models as possible, which have the least model inferencing time or computational time, so on and so forth. So this is just to give you an example. We work with these 3 models. Kannan is a very simple model. There's not much hyperparameter tuning that you need to do in Kannan's, but we just considered that because for the proof of completeness, and ResNets and XGBoost, of course. So that is what we did as well. So just to give you an idea, doing a combination of Bayesian optimization and direct search, or model-based optimization and direct search, we get a good improvement in terms of our hypervolume. And you see this. This is across all data sets, not just one. So, and just going on to, I'll just quickly discuss about another application and move on to some theory. So in the interest of time. So here we are looking at the same framework in revenue maximization. So when you actually go to retail outlets, you have seen, do you see promotions or discounts? Say in the month of December, you have a lot of discounts, right? And you are actually, people have this clearance sales where 40 to 50% of the items are given on discounts. Or if I'm pricing a shirt at about 500 rupees in the regular time, during clearance I sell it off at about 250 rupees. So the clearance is what you see during this time. So you're pretty much so this is like the demand versus price here. As the price reduces, your demand is huge. This is a very conventional setup in any retail optimization firm. And if you notice, it is very similar to a sigmoid or an inverse sigmoid. And you kind of have an S-shaped curve of this demand with respect to price. And the main important thing that we're trying to optimize is the price times the demand. I've just put this problem in a very simple term. You also have variables on inventory. You have some variables on replenishments. So you have, say you have 1,000 units of inventory or of a t-shirt available today. It kind of reduces the next day, right? So you have to put in some replenishments or stocks. So all those things are there. I've just not indicated. So the main thing that we are trying to do in this case is this demand. I have just assumed that the demand follows this pattern, but in principle, it is not. What happens is the demand is given by data, and we have data. We have data with respect to demand and price. Say sales or demand, they're pretty much the same. And this is how it looks like. what we tried to do in this work was we tried to fit functions for this demand, and we tried to optimize this revenue. So it is again the two-level optimization that I'm talking about. So you have a machine learning problem, you have a revenue maximization problem. Yes. This is not Bayesian optimization. So here you just fit some functions which are of this form, piecewise linear functions or quadratic functions or cubic functions, and on top of it you optimize just pure regression, nothing more, absolutely nothing more. And how you do the regression is another thing, but it's nothing but regression. So yeah. And you're optimizing this revenue, and this revenue happens also to be convex. The revenue is also convex if you use some PLFs, piecewise linear functions. If you're using, the revenue is also convex beautifully. So we have some theory for that, but no, when you have piecewise linear functions, when you have PLFs, you have convex objectives. So, but definitely not when you have cubic or other polynomials. So the other thing that is interesting here is we look at it from a multi-objective angle. So in India, we have this MRP, so it's maximum retail price, where you can't sell a product beyond a particular level. But that doesn't mean to say the product cannot be priced at different levels in two different regions. You can say you can have the pricing to be non-uniform in, say, Delhi versus Bangalore or something like that. So one of the problems that is very common in literature these days is the fair pricing. So it has to be same. The price has to be very similar across multiple segments. So why I'm interested in, I'm not a business person, but at the end of the day, this problem is very crucial from a business perspective, and they are looking at reducing the bias in pricing, or rather, they want to have more fair prices. So the second objective becomes crucial there. So this is the regression problem that he was mentioning about. So where you naturally have to fit some piecewise linear functions to data, and then you have objectives which are revenue maximization or cost minimization, and of course fairness in terms of pricing. Say different segments should not have different prices, so you should not have stockouts. So you can't say that inventory in this particular region, I mean, it can't be zero, right? I want to purchase something, the inventory is zero, I don't have any products available because they've already been sold. So it shouldn't happen. So that's another important thing that we're talking about. So this is just to say that we are fitting PLFs here and there's some theory behind it. But nevertheless, all we tried to do here was we were able to solve this problem and this joint problem, and we presented some numbers saying that, okay, we have, and it's not about progress. We are not comparing with any algorithms. We're just trying to solve this problem, which is present in literature. That's pretty much it. So, yeah. RL you can in at least definitely hyperparameter tuning. So I would actually so at least the hyperparameters that I learn and keep updating. Okay, I'll make it very simple. Bayesian optimization and direct search, when to use. I think RL would be a very good framework to figure that out. So other than that, I don't think it is very adaptable, my framework to RL, at least in the current setup. So I'll have to do a little work on that, but I don't think in the current setup it is adaptable for RL. So, but definitely we would want. So we are doing something just based on time or some alternating back and forth stuff between Bayesian optimization and direct search. But if we can learn something using RL, I think that will be very beneficial. So when to use BO, when not to use BO, it's very beneficial. Yeah. So I mean, this is just a little bit of a prelude which I want to give before getting into the theory. So here we have model-based methods, we have search. For model-based methods, it could be Bayesian optimization or trust region methods. So we have theory for one of those classes, so which I'll talk about now. And I'll also talk a little bit about stochastic approximations, for which I definitely need your input. So I'll talk about that as well. So anyway, so by model-based methods, I think this is very familiar to several optimizers here. So you have a trust region method where you actually, this applies to the hyperparameter tuning problem or the HPO problem that I was discussing about. So where at the outer level, this is the outer level problem. So for which you actually can use a trust region method technically. And the trust region method, of course, you need the gradients and you need the Hessians, and you actually operate within some region of trust, and you try to optimize this model within that region of trust. And if you get sufficient descent, you update. Otherwise, you don't. You shrink the trust region radius and so on and so forth. And I think this is very common. And what in our case we do is we don't have the gradients or Hessians. We have black boxes. We don't have the gradients, be it hyperparameter optimization or anything for that matter. So which we approximate these gradients by GK and HK. We use interpolation to do that. By interpolation, I'm just saying, say you look at 3 points, and you try to fit a quadratic to those 3 points. That is interpolation. So in a one-dimensional case. So you do that in n dimensions with n into n plus 1 by 2 parameters. That is estimation of your GK and HK, which will replicate your gradients and Hessians for a sufficiently small trust region radius. So that is actually the theory. They are the Taylor's bounds. So within certain trust region radii and certain Lagrange polynomials, so certain assumptions on Lagrange polynomials, you can actually ensure that the interpolation model that we build is going to be very close to the actual Taylor series expansion. So, and this is a basic trust region method for derivative free optimization, where if you get sufficient descent, you actually increase your trust region radius. If you don't get sufficient descent, you decrease your trust region radius, you shrink it essentially. And if your points are not good, you keep the trust region radius as is, add better points. And if none of these things work, keep shrinking your trust region radius till you get descent. So this is a very adapted way of doing your TR. And doing direct search, it's just, let me make it very simple. Direct search is just using coordinate directions. So you don't use any gradients. You scan it, say, in the case of 2 dimensions, 1, 0, 0, 1, minus 1, 0, and minus 0, minus 1. All those directions. And you see if there is a descent. And by the way, it is guaranteed using coordinate search that you will get descent. I mean, but it'll take a long time. Just that instead of taking a very nice gradient step, you take a zigzag curve slowly and steadily. So what do we do when combining both? What the main crux of doing this is, when your GK or norm GK is less than a particular threshold, you actually switch to direct search, and you try to take the benefits of direct search, put it onto this, and go on and go back and forth. So that is pretty much the hybrid algorithm. And okay, how does the convergence work? So if your gradient is less than a particular threshold, it tells you that your descent is not happening because of either the points, the spacing of points, or because your model is not good even if you have good points. So for which actually what happens is, luckily, using coordinate directions or any orthogonal directions from direct search, even if you don't get descent, you actually improve your model's poisedness geometrically. So we've been able to figure this out, and based on which your trust region method actually does better. So the back and forth thing helps. So you're taking the benefits in terms of the theory in both TR and DS. So that is the key takeaway of this theorem. So if you have any questions on the theory, just let me know. We can have a discussion offline. I'd be more than happy to. So on lastly, a little bit on the stochastic approximation front, going back and forth. So actually speaking, why I mean stochastic approximation is the learning problem. Technically, we don't solve the learning problem to its fullest in one iteration. We just take a gradient step, go to the other problem at the outer level. So which actually kind of mimics the stochastic approximation. Not a sample average approximation, but a stochastic approximation. So in short, all these problems can be cast as a joint setup in X and theta. And theta star is the solution to a learning problem, and X is nothing but your original set of decision variables. So what we do here is where the stochastic approximation kicks in. So there is some error with respect to my learning problem, which is WK. You update your theta k, or rather you update your learning parameters based on projected gradient descent for any of these methods. And you actually go to theta star and you update your xk based on this. So this is a back and forth approach. And we've been able to show theoretically that under certain conditions of pseudo-convexity, not convexity, pseudo-convexity. So this is very common in optimization of ratios. Say you have lift versus drag, or something like you want to minimize the ratio of maximize the ratio of fuel economy and acceleration time, all those things. So when it comes to ratios, they happen to be pseudo-convex. And under pseudo-convex cases, under some assumptions on step sizes and Lipschitz continuity, you're actually able to prove that the sequence converges to optimality. So it's a very simple stochastic approximation scheme and applied to pseudo-convex problems in the case of joint optimization and learning. But I have a lot to learn. I think we can expand on a lot of problems using stochastic approximation. Yeah, I would need your inputs on that. This is a very simple case, but I've not been able to go beyond the case of pseudo-convexity. So you have a lot of non-convex cases which I don't have an answer for. So maybe we can discuss a little bit on that. So yeah. And okay, where I'm going ahead with this is I want to look at problems related to security and safety. So you have all these. Say, for instance, you are in an industrial setup, and there is a grinder. There's a big grinder or a miller, and someone is operating that miller, and you have sensor data and for safety, where exactly is the person going when, and based on the logs, there could be faults and issues, right? The person could accidentally fall into the miller, and there could be issues. All those things we want to just minimize, of course, costs, and we also want to minimize the risk or threats. So we are looking at those problems in surveillance. So that is pretty much where I'm going with this setup. The same algorithms, the same, what can I say? The same framework extends. So, yeah. Not yet. Not yet. So I have not put in cyber security yet. I've just put in physical security. Cyber security, I have not. I don't have, what can I say? I don't know, maybe. Maybe not. I don't know about the domain, so frankly. So I think that's pretty much what I had for today. So I think the time is for questions.
So let us thank Professor Aswin again, and thank you all for participating and involving in the discussion. See you next time. Thank you.
Thank you.
Thanks.